Hello. In this video, we're going to look at some optimization problems. Now, you've already done optimization problems when you were learning about quadratics. Finding a maximum or a minimum of a quadratic function was as simple as finding the vertex of that function. And we know that we can find a vertex using a derivative. Where is the slope of the function equal to 0, or where is the derivative equal to 0? So with that information, we can now find maximum or minimum points on functions that are more complex than just simple quadratics. So let's look at an example here where we're looking for a point on a particular line that is closest to a given point that is not on that line. So to help out here, I'm actually going to make a little sketch of what this looks like. So that line crosses the x-axis at 6, it crosses the y-axis at 2, so it looks something like this. And then the point, -3, 1, is going to be over here somewhere. So this is the point -3, 1. And what I'm looking for is I'm looking for some point on this line where the distance is closest, so where it's going to be a perpendicular. So this is some unknown xy, and we are looking for the coordinates of that point where we want to minimize the distance. So closest to the point, minimize distance. Now first up, whatever it is that I'm trying to maximize or minimize, I need that in an equation. And it needs to be my dependent variable, basically my y, so that if I find the vertex of this new function, I'm finding the highest possible or the lowest possible value of that variable. So I'm going to let d equal the distance here. And so I need a formula for the distance between these 2 points, the -3, 1, and the unknown point xy. But I don't want to use 3 variables. I don't want dx and y. So I want to express the point x and y in terms of just one of those variables. Now, traditionally, we would take this equation, we would isolate y. I'd get y equals -1/3 x plus 2, and I could use that in place of the y value. But then I have a fraction, and there's actually no mathematical reason why I have to isolate y. So instead, what I'm going to do here is I'm going to isolate x, because then I don't have fractions. So I have x equals -3y. Well, I'm going to say it is x equals 6 minus 3y. So this point, instead of being the point xy, is the point 6 minus 3y, y. And I want the distance between that point and -3, 1. So the distance formula uses square root and so on. I also don't want a more complicated equation than it needs to be. So instead of using the distance formula with the square root, I'm just basically going to use the Pythagorean theorem. I'm going to say that there is some vertical distance between these 2 points and there is some horizontal distance between these 2 points. And that creates a right triangle here. So I know that d squared, so said quite generally, d squared equals delta x squared plus delta y squared. But that means that d squared equals, well, the change in x's is 6 minus 3y minus -3, so plus 3 squared. And the change in the y values is just y minus 1 squared. I'm going to simplify this a little. So d squared equals 9 minus 3y squared plus y minus 1 squared. Now, you can distribute this whole thing, and then you have a nice polynomial, which is going to be very easy to derive, but it's actually not super hard to derive as is. And like I said, I definitely don't want to take the square root of both sides. That's going to make it harder to derive. If I leave the d as d squared, then I can just use implicit differentiation. So I'm going to derive d with respect to y. So I get 2d times dd dy equals 2 times 9 minus 3y times -3 plus 2 times y minus 1 times 1. So just the chain rule there. And each of these is times dy dy, so it doesn't, I don't need to worry about it. Handily, all these 2's are now going to just cancel out. So I can simplify what's going on the right-hand side of this equation. So d times dd dy equals -27 plus 9y plus y minus 1, or just 10y minus 28. So what that means in terms of the derivative here is that the derivative of the distance with respect to y is equal to 10y minus 28 all over d. Now, I could replace this d with the square root of 9 minus 3y whole squared, etc. But what I'm interested in here are the critical values. In other words, where is this slope equal to 0? And the denominator isn't going to impact that because this denominator is always greater than 0. So the denominator is always greater than 0, so I'm not going to get any critical values there. I know the denominator is always greater than 0 because it represents the distance between this point and this line. And because the point is not on the line, that distance cannot be 0, and it has to be positive. So all I'm looking for critical values are when does 10y minus 28 equal 0? Well, that happens when y equals 28 over 10, or in other words, 2.8. Now, that's not the answer to the question fully because we wanted to know the point on the line. So in other words, we want the x and the y values. So x was equal to 6 minus 3y. So if I do 6 minus 3 times 2.8, we get negative 2.4. So the answer to the question is that the point negative 2.4, 2.8, is the closest point on that line to negative 3, 1. Now, there's one other thing we should do here. Logically, in this scenario, that must be a minimum. So I know that I found a point where the slope was equal to 0. That could be a minimum or a maximum. Logically, here it has to be a minimum because there is no maximum distance. I can find points on this line that are going to be infinitely far away from the given point. But I need to include some indication that I have verified that this is in fact a maximum. Or a minimum, sorry. So we're going to verify that it is a minimum. There's two different ways to do it. One of them involves taking the second derivative. And this particular function, the second derivative is going to be kind of icky because we would have to do it implicitly. It's going to use the quotient rule or whatever. So I'm not going to do the second derivative test for this one. The other one is to use sign tables and figure out areas of increase and decrease on either side of that critical value. So in other words, at 2.8, when y equals 2.8, I know that the slope is 0. So if I take some value that is less than 2.8 and test it, is the slope positive or negative? In other words, is the derivative positive or negative? Now, since the denominator d is always greater than 0, all that matters is whether the numerator is positive or negative. So in other words, is 10y minus 28 positive or negative? So if I take some y value like 0, that is less than 2.8, 10 times 0 minus 28 gives me a negative number. And if I take a y value that's bigger than 2.8, let's say 10, 10 times 10 minus 28 gives me a positive value. So that means the derivative is negative to the left of this value and positive to the right of it, which means that the original function has a downward slope and then an upward slope. Because of that and the fact that there's a 0 here, this must be a minimum. So I have verified that this is in fact a minimum value instead of a maximum value. We're going to do one more example, and in this one, I'll show you the other verification, the second derivative test for verification. But again, we're going to be looking for a minimum. So what is the minimum surface area possible? So minimum surface area means I need an equation for surface area. So the minimum surface area possible for a cylindrical container, so I need the formula for area of a cylinder. So the surface area of a cylinder is 2 pi r squared, because there are two circles on either end of the cylinder, plus 2 pi rh, which is the lateral area, the part that will unfold into a rectangle with a height of h and a base of the circumference of the circle, 2 pi r. So I want to know the minimum surface area possible for that cylindrical container. Again, I have too many variables. I have a, r, and h here. I don't want all those. So I need a way of relating r to h. And that's where the fact that the volume is fixed at 500 centimeters cubed comes in. So the volume of a cylinder is pi r squared h, which has to equal 500. So I can isolate h here. H equals 500 over pi r squared, which means I can substitute that into my area formula. So area is 2 pi r squared plus 2 pi r times 500 over pi r squared. which I'm going to simplify before I derive. So A equals 2 pi r squared plus 1,000 over r, but I'm just going to call that 1,000 r to the negative 1. Because now when I derive it, it's just a simple application of the power rule. So to find the minimum, I'm going to find critical values of the derivative. So derivative of area with respect to the radius, dAdr, is going to be 4 pi r minus 1,000 r to the negative 2. Now at this stage, to find critical values, it is going to be helpful to express this as a fraction. So 4 pi r minus 1,000 over r squared. For a common denominator of r squared, I'm going to turn this into 4 pi r cubed over r squared. So I get 4 pi r cubed minus 1,000 over r squared. So my critical values here, well, I get a critical value that r cannot equal 0. That was a critical value right from the start because it was a domain restriction that r cannot equal 0. But I also get critical values when r cubed, so in other words, r is going to equal the cubed root of 1,000 over 4 pi, so 250 over pi, which is approximately, if I do that division really quick, so 250 divided by pi, and then the cubed root of that, we get about 4.3 centimeters, roughly. Yeah. So that's our critical value. That's where I would be expecting to find a minimum surface area, but it could actually be a maximum surface area. So again, I need to verify that this is a minimum. And for this one, I'm going to use the second derivative test. So to verify that it's a minimum, the reason I'm going to use a second derivative test here is I can find the second derivative just with a very simple power rule application. Going back here, so the second derivative of A with respect to R is equal to 4 pi plus 2,000 r to the negative 3, or 4 pi r cubed plus 2,000 over r cubed. Now, the thing to note if I'm doing the second derivative test is I want to know, is that second derivative positive or negative? In other words, is the curvature upwards or downwards? So in this case, r cubed, because we're dealing with a radius that has to be positive, this is always greater than 0. And the numerator, for the same reason, 4 pi r cubed is always going to be greater than 0. Adding 2,000 is always greater than 0. Therefore, the second derivative is greater than 0. Now, I don't need it to be greater than 0 everywhere. I just need it to be greater than 0 when I plug in my critical r value, so the 4.3 centimeters. But in this case, because it actually is positive everywhere, that means that the curvature is positive, and that means that this must be a minimum. So this is a minimum. The minimum occurs when the radius is the cubed root of 250 over pi. However, that's not the answer to the question. So let's go back and look at the question. What is the minimum surface area? So the minimum surface area is the answer. So the minimum area is going to be the value of the area when r is that 250 over pi cubed rooted. So storing that in my calculator, I'm going to calculate what is 2 pi r squared plus 1,000 divided by r. And we get an area of approximately 349, when we round to 3 significant digits, centimeters squared. So that is the approximate area, the minimum surface area possible for a fixed volume.